Alright, this is the third and final hour of Physics 1C for September 13th, and we're going to be talking now about something that's connected to electric field lines, which is called electric flux. So, electric flux is a quantity that we get by taking the electric field and multiplying by an area. That's the simplest thing I can say. Suppose that I have some electric field lines in space, in an area of space. So I've got some field lines here. What's creating them? We don't really care at this point. Just know we've got some electric field lines. So there's our electric field. And let's say that we take like a sheet. And let's draw it. Actually, let's use this. Okay, I don't know why I thought that would work. We're just going to have to draw it ourselves. So we're going to take a sheet. No. Click on one of these. Go like that. Okay, so we take a sheet, and we're going to orient it so that it is perpendicular to the field lines, and we're going to say that it has an area, that A stands for area, has an area A. We're going to take that sheet, and we're going to put it into our electric fields, like right here, like right here, okay. And we're going to make it so that the field lines pierce the sheet perpendicularly. Okay, so if the field lines go straight through like this, then we can define electric flux. The symbol we use for electric flux is phi. I guess they didn't want to use F because F is for force, so they used a phi. And I hate drawing this every time, but that's what we use. It's like an I with a circle around it. That's the capital Greek letter phi. I'm going to put an E down here. Do we need to do this? I don't know. To represent that it's electric flux, because we're going to learn about magnetic flux way later in this class. And in this case, if the area is perpendicular, so I'll just say that this is, the field lines cross through this perpendicular, that means, where can I draw it? If this is a line that's drawn within the plane of the sheet of paper, the electric field lines make right angles. They come straight through it. In this case, if you take the size of the electric field and you multiply by the area of the sheet, this gives you the electric flux. You take electric field and you multiply by area. Okay? Take electric field and you multiply by area. But you may ask, what happens if that sheet isn't perpendicular? What if the sheet is shaped in such a way that it's sideways? So let's take our field lines. Okay, it didn't let me copy all of it, but I can delete some of this stuff. No. Delete. Okay, so what if our field lines pass them through something that is not perpendicular to it? So for example, let's say that I have a sheet, and my sheet is sideways, so it's situated. I'm just going to draw it like this. So if we take a sheet, and let's say that it's oriented like sideways, so kind of like this. Now, in this case, the flux is going to be equal to 0. So when the plane is perpendicular, you get some flux. When the plane is parallel to the lines, like this, so assume that these field lines just keep going, you get a 0 flux. And when it's oriented something in between, you get a flux that depends on the cosine of the angle between the two of them. So if I have a situation, for this one I'm going to draw actual arrows because I'm going to need it. So the general scenario then is, suppose I have some field lines. So there's my electric field. Make it seem somewhat three-dimensional if we do that. So let's say those are my electric field lines right there. And now if I take a plane, and I place it inside of here, but I put it at an angle, so let's say that I make it at an angle like this. And just to keep things simple, if it's okay with you, let's imagine that I draw a sheet that has area A, but I just look at it edge on, okay? So this is a sheet. I still need to make it somewhat three-dimensional, probably. So let's do that. So here's my sheet. I've tilted it at an angle. I'm not a big fan of how I did this with the 3 dimensions, but just, I think it's kind of okay. So now I've tilted it at an angle like this. And now let's say that we draw a vector. I'll make this one green. And we're going to draw a vector that's going to be perpendicular to the surface of my sheet, okay? And I'm going to call that vector an area vector. This is going to be an area vector. And it is perpendicular to the plane of the sheet. And by the way, these sheets that I'm drawing in here, they're all kind of imaginary. They're not real objects. They're just imaginary surfaces through which we're going to describe the flux. I should have said that to begin with. So, suppose that I have this situation where the electric field lines are like this and the area is like this, so that they make an angle here that's equal to theta. That is to say that my field lines point this way, right? My area vector points this way, and the angle between them I'm calling theta. Then the flux in this scenario, and this is the more general version, is going to be equal to the dot product of the electric field with the area vector, because you basically want the projection of that field onto the surface. I'm not looking at the right chat. No one's saying anything, but I'm not looking at the right chat. And if you don't remember, when you do a dot product, when you have two vectors and you multiply them with a dot in between them, unlike a cross, then you get EA times the cosine of the angle between the two of them. And that gives us our definition of electric flux. Very specifically, this is for a uniform field through a flat surface. So uniform means basically constant, not changing, and flat surface. Yeah, Justin, sure. Now that we've defined what it is, I'll definitely compare it to something else, if that's okay with you all. So does what the definition of what the flux is, does it make sense? In terms of what I mean, if you don't understand what flux is, that's fine, but do you understand the things that go into it? Size of electric field, the area of the surface, and the angle between the two of them. Anyone have any questions about that? So let's do an analogy. Solar flux. So let's say you have a home, okay? And your home is going to be a very, very simple home. It's going to be shaped like a rectangle. And on the roof of your home, so it's a home, so let's put a door in here. I don't know, a window or something. So on the top of your home, you've got solar panels, okay? But these solar panels can't move. So some solar panels can kind of like tilt mechanically, but we're just going to say that these solar panels on top of your roof, it's just flat, okay? And the solar panels, what do? Well, they absorb light from the sun and they turn it into electricity. Certainly you all probably have already knew that, but in case you didn't, that's what a solar panel does, is it takes light from the sun And using something that was discovered by Einstein, well, not discovered by Einstein, that was theoretically explained by Einstein, called the photoelectric effect, it turns light into electricity by knocking free electrons from different substances. So if the sun is directly overhead, right, it sends out its rays, right, and those rays, when they get to the Earth's surface, they're basically all going to be parallel. Would you agree? So if these are rays from the sun, once they get to the surface of the Earth, they're basically parallel to each other, right? So if this is what things look like at noon, let's say this is noon, local noon, then your solar flux is going to be at maximum when the sun is shining straight down on them, right? Would you agree? You're going to get the most electricity per minute or per second. The most power output of your solar panel will occur when you get the maximum flow of sunlight into the solar panels, i.e. when the flux is the highest, right? Because notice that what is the thing that corresponds to the area in this case? It's the solar panel or the roof, right? And just like we did in this picture right here, we can draw an area vector, right? I can come to my roof right here and I would say my area vector is going to go this way. My flux lines from the sun, let's use like an S with a, they come in like this. S. We're actually going to use this later on for something called the Poynting vector. Anyway, so turns out these rays of light coming from the sun, they actually have electric fields in them, as it turns out. Anyway, doesn't really matter. Point is, if the area vector points down and the sun's flux points down, this is when you get the maximum, you know, the angle between the two would be 0, basically, right? So cosine of 0 is 1. You get maximum flux. Okay, so just to kind of like, that's going to be the maximum flux, right? But what happens when we move the sun to, like, earlier in the morning over here? So now the rays from the sun that come in are going to be hitting your home kind of more like at an angle now, right? So now now the rays from the sun are coming in kind of more at an angle. I'll make this kind of extreme. So without the sun directly shining down on it, now you get a reduction in the amount of output of energy from your solar panels, right? You get a smaller amount of energy from your solar panels. How much less? You take the cosine of the angle between the angle at which they're coming in and this angle right here. So basically you would draw this line like this. You'd find the angle right here. You'd find what this angle is here between the lines that are coming in from the sun and the area vector here. You take the cosine of that angle, and that would tell you exactly how much the efficiency of your solar panels is going to be reduced based on the time of day. You can even write an equation to describe what that is how it's going to change over the daytime, right? And of course, whenever the sun's rays are coming in straight like this, you get no solar flux, right? So the solar flux is going to depend upon the angle between the line between the sun and your house. And does that make sense? Electric flux is the same concept, except that instead of using the invisible rays of light from the sun, you have to use electric field lines that we just finished talking about. And what we're going to find out next is that the number of electric field lines is going to be directly proportional to the flux. Okay? Anyone have any questions? So let's do a problem. I was going to do something kind of simple, but... Oh! Flux can be positive, negative, or 0, by the way. So flux can be positive, negative, 0. Because if the angle is greater than 90, does this have to do with the curl and divergence theorems? Kind of. Kind of. We'll get to that a little bit later. Alright, let us do a problem. And I was going to do something really simple, but instead, we're going to do something slightly more complex. Alright, so we're going to do a uniform field through a triangular prism. That's what we're going to do. So we're going to kind of make this one up on the fly, but I have a problem in mind that I'm basing this on. So we're going to start off with a triangular prism. It is going to be a right-angled triangular prism, so one side is going to be straight and one side is going to be slanted. We're going to make it a 30, 60, 90 triangle. Alright, so right triangular prism, right? Right angle right here. We need some dimensions to this object. So let's call this dimension over here h. Let's also draw in three-dimensionally like the stuff that you can't see. So there's also going to be a line that comes kind of back here, and there's going to be a line that drops down like right here. And actually what I should be doing is I should copy this one, and I should really paste it back here. Oh, it actually turned out pretty well. It's pretty close. Not exactly perfect, but hey. Alright, oh, and there's one more line, right? There'd also be a line that would connect from this one to this one. Okay, so there's our picture. Kind of looks okay, I guess. So let's say this side is H. Let's say this side is L. And since this is the base, we'll call this side B. Okay? And we're going to place this into a uniform electric field. And let me label some things for the axes here, too. So let's do, like, green shapes. Let's do axes. So I'm going to make it... You can see just how not straight those lines are now. It's funny. I'm going to make it so this is our axes, okay? So this is the x direction. This is the y direction. And we're going to say that throughout this region of space... Here, let me try and take this whole thing and just move down some. I'm going to get a lot of room here. Okay, so in this region... Oops. There exists a uniform electric field what is going on with my handwriting today? F-I-E-L-D of. So I'll give you the vector definition of it. It's going to be E is equal to. I kind of just want to use the symbol, but we don't have to, right? All right, let's give it a name. Nah, I can use the symbol, right? Let's use the symbol. I don't want to use numbers. So it's going to be equal to E, which is going to be a constant times I hat. Okay. Uniform E field of E times I hat. That's what the size of our electric field is. And what does that look like? Well, if it's E times I hat, then that means that it looks like this. Let's use blue. It's basically just a bunch of straight lines. Like this. That's our electric field. Hopefully that doesn't obscure the diagram too much, but that's our electric field right there. One other thing we need on this picture is a z-axis, don't we? Definitely need a z-axis. So we're going to make it so that the back edge of this object is sitting along the z-axis. Okay, so that's the positive z direction. That means that the back face of my cube, my triangular prism right here, is in the zy plane. Okay, one last thing we need is an angle. We're going to call this angle right here theta. And we're going to say that theta is equal to 30 degrees. All right. We may remove the electric field lines at some point, in case it becomes too hard to see what's going on here. So we want to find the net flux through the cube. This will allow me to talk about some of the things about flux that I haven't talked about yet. Okay, so this is the problem. Find the net flux through the cube. Okay. I think we have all the dimensions we need there, right? We need this side. But let's leave it undefined because we can define it in terms of the other variables. So theta is 30 degrees. So let's look at this one by one. Let's start off by looking at the back face of the cube right here. So phi through, we'll call it the left side. Okay. So some things I have not told you yet. First thing I haven't told you yet is how to draw the area vector. How do you draw the direction of the area vector? And the answer is, this always points out away from the surface. If you have a closed surface, your area vectors are going to point away, okay? So let's use a color like purple for this. And on the back face then, the direction of the area vector is going to point like that. Okay? Do you all agree with that? That this would be, I mean, for this back surface back here, if I want to draw a vector, uh-oh. Is Discord doing okay? Can you also hear me okay? Looks like yes. So, on this back surface right here, would you all agree that the area vector points to the left? And can you see why? Yeah, there was very clearly like a hiccup in the internet. I heard it there. Okay. So area vector points away from a closed surface, and yeah, for the back surface it points like that. Okay, so what is the angle between the electric field, which points to the right, and the area vector that points back like this? What's the angle between the two of them? 180, that's right. So it's going to be E times whatever that area is, times the cosine of 180. That's our definition of our flux. What's the area on the left-hand surface? What's the area of this back surface right here? It's a rectangular prism, so it's L times H, right? So this is going to be E times L times H with a negative sign, right? Easy enough. Okay. I'll leave this area on here, I guess. All right, what about if I come to the front surface? Let's do the front surface. This is going to be the front side, okay? What direction do I draw the area vector on the front surface? On this surface, how do I draw? I remember, where did I say it? Somewhere. Area vector, perpendicular to the plane of the sheet, right? So I've got this sheet. The front sheet is facing like this, basically, right? It's hard for me to, but it's, you know, it's kind of in the plane of the page, right? So that means that when I want to draw a vector for the front sheet, it either has to come out towards me, or it has to go in towards the screen. Either comes out or in. But I said that if you have a closed surface, the area vector has to point away, right? So what do you think? Should I put a vector out or in? Out of the screen. You're correct. So for the front surface, this is my area vector. It should point along the positive z-axis, right? Here, let's subscript left. We'll call this A front. Okay. Then, this is again going to be E. We'll label this A front. And now, what do I put in here? What's the angle between the two of them? This is the angle between, yeah, it's 90, right? And again, it's the angle between E. The electric field points to the right. The area vector in the front points out. So it's a right angle. It's right here. It's hard to see, but that's a right angle right there, basically. So it's 90 degrees. And what's the cosine of 90? It's 0. So the flux through the front is 0. Because none of the electric field lines actually penetrate that surface. Okay, what about the back? What's the direction of the area vector for the back going to look like? It's going to have to be the opposite, right? It's going to have to go into the screen like this, right? But again, the angle is going to be 90 degrees. This angle is 90 degrees here because that vector is going into the page and the electric field is in the positive x direction. So that means the angle is going to be 90 again. So the flux through the back, and this is a back, I should say. The flux through the back is going to be E area back cos 90 again. Very repetitive, but whatever, it doesn't hurt. Flux through the back, also 0, okay? Cool. Now, to do the rest of these, are you all okay if I get rid of these vectors? Because I think that it will help. So, you're going to have to be okay with it. Alright. Can I just delete those? We can. Delete this.
I'm sorry I'm a little behind on this, Professor. Can I ask one?
Yeah, ask a question, go.
I don't understand that flux in the back, how the cosine is 90 degrees. The cosine between the field and the area vectors didn't look like 90 to me. I don't know.
Yeah, it's not going to look like 90 because I'm drawing it on a two-dimensional surface. But
that's 30 degrees.
What? No, listen. So when I draw a line, the back surface, right, it's flat. It's in the plane of the page, right?
Oh, I see what you mean. You're not talking about the top surface there. You're talking about the surface that's behind where the B is on the bottom.
You got it.
Okay, got it.
Okay, cool. All right, so what do we have left? We've got the bottom surface. Can any of you tell me before I even do it? What's the direction of the area vector for the bottom surface? Type it in the chat. What's the area vector for the bottom surface? It's down. Right? What's the angle between this area vector for the bottom and the electric field? 90. So what's the flux? You could say 270. That works too. You get the same answer. So what's the flux? 0. Exactly. So the flux through the bottom also equal to 0, basically for the same reason, because there's a cosine 90 in there. Okay. All right, so we've got all those. That's fine and dandy. What I'm going to do is we're going to take all this work and we're going to move it over here. We're going to make it a little bit smaller because I want to keep this picture up here. So far, only one of them has any flux. Every other one was 0, right? Okay, so what are we left with? I think there's only one more, right? What's the one surface we didn't do?
The angled surface?
That's right. We'll call it the angled surface, as you said. It's the flux through the angled surface. Now, okay, again, we need to draw a vector, right? For the area vector. Let's draw it like this. I need to make this perpendicular to the surface, but it's three-dimensional. It's so hard. Okay, so there we go. Hopefully that's perpendicular to my surface. And that's going to be my area vector. We'll just call this one A. I don't want to write more subscripts. That's my area vector. And now we want to do two things. We got to calculate the area, and then we need to find the angle. So how do I find this angle here? Theta. It's not theta, sorry. How do I find this angle right here? For me, what I would do is I would draw it like this, just to make it simple. Draw a two-dimensional version of what's going on. Because I know that my electric field lines are coming this way, right? Where that's parallel to the bottom surface. We know this is defined as theta. And the angle that we need, if we draw our area vector like this, the angle we need is this angle right here. I'm going to call it phi. And I would argue in this case that phi is equal to 60 degrees. Do you all agree? If this is 30, that phi is going to be 60? Okay, so that's what we're going to use. That angle, 60 degrees, is going to be the angle between our E and our A. So I'll just put that down here so you can still see it. All right. So 60 degrees is our angle, so we're going to have the size of our electric field, which is its E, right? multiplied by the area of the angled portion, and then we have to multiply that by the cosine of 60. Now, what is the area of the angled portion going to be? Well, it's a little bit tricky, because we didn't define how long this line is right here. But if we did things right, so what I would argue is that the length of the slanted side here, right? If I have a triangle that is a right triangle where this is a 90-degree angle and this angle right here is 30 degrees, and this side is h and this side is b, then I would argue that this side over here is going to be h divided by the sine of 30. Would you all agree? Yep, okay. So you guys checked it, looks right. So that means the area of the angled side then would be that side, which is h over sine 30, multiplied by, I mean, this is basically a rectangle right here, right? That's a rectangle, with one side being h over sine 30, this diagonal side, and the other side being the length L, which goes into the screen, right? So it's that times L. Putting that together, how are cosine 60 and sine 30 related? I'm pretty sure they're both equal to a half. Those are the same, right? So it turns out that the flux through the angled surface is equal to E times H times L. Positive. Which means the net flux is equal to what? If I want to add up all the fluxes, they're scalars after all, we can just directly add them. The net flux is equal to negative E times L times H, plus E times H times L, plus 0 plus 0 plus 0. So this is also 0. The net flux is 0. But it allowed us to talk about these little details of how flux works, which is why I think that's a good problem. And it's a better problem, I think, than what your book does, because what your book does is it just looks at the flux through a cube. And I think the flux through a cube covers a lot of these ideas, but it doesn't cover the angle portion of it, so I wanted to do that. I love this because it's just so neat that it's exactly 0, no matter what the shape of the object that you put in here is, as it turns out. It works for a rectangular prism, a cube. You could put a sphere in here, although the calculation would be a little trickier. You could put a sphere in here, and you would also get 0. It turns out that any time you have a uniform electric field in a region of space, the left cover. Oh, is this blocking? Here, I'll just scroll down. Is that better? I'm sorry about that. Any closed surface placed into a uniform electric field will have a net flux of 0, basically. That's how it works. We have so little time left, but I'm going to try to get Gauss's law. I'm going to squeeze it in. We're at least going to squeeze in what Gauss's law is. Okay, so the next thing to ask is, what about non-uniform fields and curved surfaces? So for example, what's an example of a non-uniform field? How about the field of a point charge? We've talked about this so much. If I have a point charge, the electric field is not uniform, right? If I have a point charge, the electric field is given by this expression. Right? Not uniform. It doesn't point in the same direction everywhere, and it varies as 1 over r squared, so it gets weaker the farther away that you get. So suppose I have an object like this, and suppose that I want to find the flux through like a curved surface. So maybe I have some curved area that I want to look at, right? And then I go through and I draw my electric field lines, we know that the electric field lines point something like this. They do stuff like this. And now what you have to do is at every point on your surface, you have to draw a tiny little area vector. And that area vector we call dA. We say it's going to point perpendicular to the surface. And then you have to look at the angle between the two of them and say the flux through that little piece would be E dot dA. And the angle between these things may change at every point. You know, I come to this point right here and I draw my area vector. From this point, maybe the angle's down like this. I don't know. It changes at every point, depending on how the shape of the surface is. So in order to find the total flux for a system, you have to do this for every point on the surface, and then you need to sum them all together, which means you need to do an integral. Or sum, whatever you want to think about it as. And this is going to be our general definition of how we do electric flux. And I will give you an example, because that's obviously a very complicated equation. I'll give you an example. There's so many more things I want to talk about, and there just isn't enough time to talk about all of them. So we're going to do the example of the flux of a point charge through a sphere. Okay, so that's what we're going to do. Oh yeah, I forgot. Yes, this is a surface integral. Is it important that it's a surface integral? Probably. Yeah, this is technically a surface integral. That's right. There should be two lines, there should be two integrals, and there should be an S on here. I apologize. Okay. Find the electric flux of a point charge through a spherical surface. Okay. So we've got a point charge. That's our equation that we're going to use. We want to find the electric flux of a point charge through a spherical surface. So let's move our point charge down a little bit. Let's surround it with a sphere. Try to get it right in the center. Looks pretty good. And then we'll draw another line around here to make it look more like an actual sphere. Okay. So there's our sphere. We place our charge right at the center of the sphere. And I'm just going to go ahead and say that the radius of our sphere is little r. No. Does it really matter? I don't think it does. So that's our sphere. It has radius r. And we're going to find the flux through this sphere, which means we're going to need to draw field lines. So our electric field lines are going to kind of come out like this. Right? You don't need to draw a bunch of them, but there are electric field lines that go all around. What I'm going to do is I'm going to come to this point on the surface right here and say, suppose that we look at the area vector at that location. So this is the electric field vector, right? What's the direction of the area vector at this location right here? Basically, the idea is that you think about breaking up your sphere up into like a grid, basically. And at every point on the grid, you can draw a vector that you call dA. And that's just basically a surface element. Think about breaking up the entire surface into a bunch of, like, into a grid of just a bunch of pieces. And every one of those pieces will have a direction to it, right? With the DAs always pointing perpendicular to the surface. So I'm going to draw one over here, but I guess the question I need to ask before I draw it is, should I make it parallel to the electric field? Should I make it go like at a right angle to the electric field? We know it needs to go away from the surface, but what should the angle between the area vector and the electric field be here? Should it be 0? Should it be something bigger than 0, less than 0? What do you think? Should I draw the area vector like this? Should I draw it like this? Should I draw it exactly parallel to the E field? What do you think? What's the direction of that area vector going to be? We know it has to go away from the surface. We know it has to be perpendicular to the surface. But what should the angle between the electric field vector and the DA be? It should be exactly parallel. That's exactly right, yeah. So my DA has to be exactly parallel in this case. And why is that the case? Well, it's because the electric field... Can I write E as parallel to DA? Well, you know what that means? That symbol right there means parallel. E parallel to DA. I'm saying it, so hopefully you get it. So they're parallel to each other. Because the electric field line is drawn from the center radially out, right? It doesn't curve. It goes straight away, which means that it's guaranteed that it pierces through the surface so that the angle between these two is exactly 0. Okay, let's keep that in mind while we use our equation right here. Our equation says that we have to perform this integral. As was correctly stated, it is a surface integral, for which we're going to write like this. And this is going to be a integral that we do over the entire surface. So I'm going to draw a little circle around here, which means we need to integrate over every single piece of the surface. That means we have to add up E dot dA for every single point, right? The nice thing is that no matter where we choose our area, the DA will always be parallel to the electric fields, right? Because we're looking at a sphere. And the electric field of a point charge has spherical symmetry. No matter where we are, E and dA are parallel. And what that means is that if E is parallel to dA, then E dot dA just reduces down to EDA. And that's the first line of the step here. That this becomes just EDA, right? Okay, next step is to plug in what the electric field is. We know that the electric field for a point charge has a magnitude of K multiplied by the size of the charge. We're going to call the charge in here Q, times Q divided by R squared. Let's plug that into our equation. Okay, now we're doing an integral with respect to the area. What does that mean? Not important. For now, what we're doing is we're summing what this quantity equals over every single piece of my surface. Now, when you're doing a sum, you can always factor out things that are constant, right? We know that K is a constant. Whatever charge I give you in a problem is going to be a constant. But what about R? As I go over every single point on the surface of my sphere, only on the surface, not inside, right? I come to every point on the surface of my sphere, right? Here, and over here, and over here. Is R going to change? No. R is always the same, because we're summing, we're doing this surface integral only over the surface of the object, the outer surface of the object. That's all we care about. We're finding the flux through that surface, we only look at the surface. Think back to the problem we just did, if that's confusing to you. In this problem, did we care about any of this stuff inside of the cube, the triangular prism? No. We only looked at the surface, right? Left, front, back, bottom, and then the angled part. That's it. The 5 surfaces that were existing there. Only the surface itself. So, R on the surface is constant. And because R is constant, that means we can pull all of this out of the integral. And we get K, Q over R squared, and then the surface integral of dA over the surface of a sphere. Well, that's really handy, because now we don't need to actually do the integral anymore, right? What's this equal to? It's the surface area of the sphere. That's exactly right. It's equal to the surface area of the sphere. So this entire thing is equal to the area of a sphere, the surface area of a sphere, which is 4 pi r squared, right? That's the surface area of a sphere. So the whole integral is just 4 pi times r squared. Now, if you've taken Calculus 3, or if you're taking it now and you want to know how does the mathematics give you 4 pi r squared, well, you just need to create a dA, and you'll find that once you do that, you use the right version of dA, you'll also get 4 pi r squared. It's going to be something like, anyway. Oh, yeah, that's right. The r squares cancel out. You're exactly right. That's pretty amazing. Wow. It's interesting. It turns out that our answer, surprisingly, has nothing to do with the size of the sphere. That is very surprising, I think. That what we get for our answer is just 4 pi k times q. The size of the sphere doesn't matter. And then here's something else that may or may not blow your mind. Or maybe you won't care because here we are 3 hours into this class. You're probably very tired. The shape doesn't matter either. I could have chosen a cube. The math would have been way harder, but I promise you, you get the exact same answer. I could have chosen a triangle that I put around this, like exactly the shape that we put in the previous problem. And once again, you would have gotten exactly the same answer. It turns out that the size and the shape of the object that you place around your charge does not matter, and you in fact always get the same answer. Now, something else to remind you is that k is also equal to something called 1 over 4 pi epsilon naught, which means that 4 pi times k is equal to 1 over epsilon naught. So normally the way this is written is q divided by epsilon naught, and this is what Gauss's law states. This is basically Gauss's law. I'm just going to say it. We have no more time. We're completely out of time. Sorry for going over. But that's basically what Gauss's law states. It states that the flux through a closed surface is equal to the size of the charge enclosed by the box, by the surface, divided by epsilon naught. I'm going to leave you with that quote from the book somewhere here. Here we go. This is Gauss's law. This is where we're going to start next time. I would have liked to have gotten a little farther, but unfortunately, there's only so much you can really cover in these classes. Oh no. What did it just do? All I did was just try to copy-paste, and it wouldn't let me. Paste. There we go. Okay, we'll finish with that. The shape of the surface doesn't matter. The net flux through any closed surface surrounding a point charge q is given by q over epsilon naught and is independent of the shape of that surface. I'm going to leave you with that. We do not have a lecture Wednesday. We do have lab on Wednesday. If you are on the list of people that are scheduled to show up for lab on Wednesday, you need to show up. If you don't show up, you won't be able to go to the next week because we can only have 15 people in the class at a time, and we have exactly 30 people in this class. So if you are scheduled to show up, you need to show up. In order to find out who's scheduled to show up, go into Canvas, click on Announcements, or however it is that you see that. E42 for Wednesday, 9:15. Click on that, and there's the list of people that are showing up. So it's Evan Antonides, Yaman Badur, up through Justin Kim. Okay? Look at this list. If you're not on that list, you're coming next Wednesday, not this Wednesday. Is there anything those of us need to do on Wednesday if we're not showing up on Wednesday? Take that time to work on lab manual problems, finish your lab manual homework. You should, no, you don't upload anything for Mastering Physics, you just put the answers in. The only thing you're going to upload is your lab manual homework. It's the only thing you're going to upload. Okay, I'll see you on Wednesday. Thanks, everyone. I hope you all have a nice afternoon, and I will see you in a couple days if you're in lab. If not, I do have, someone asked earlier, I do have office hours at noon. In case you don't know when my office hours are, I tried to make it pretty clear. It's on the homepage here, at least for me. I don't know what you see, but I think this is what you see when you come to this page. It should show my office hours right here. They're on Discord. I know some people have shown up, some people haven't. Do you show up at 1:15 or 2:15? Great question. Didn't I put that in the announcement? You show up at 1:15. 1:15. It is in the announcement. We will be starting at 1:15 Wednesday afternoon. I know when people post stuff like this, you don't read any of this stuff. Nothing I can do about that. I wouldn't read it either. I would just see what was there. Yeah. How early do you think I should come to school to find a parking and get a class? I would come at least 30 minutes. Arrive 30 minutes early. Arrive 30 minutes before class. I'll tell you what. I have a lab tonight. It is at 6:30. I have 2 hours. I'm going to class right now. I'm not going to mess around. You know what I mean? I'm going to get there as soon as I possibly can. I'm going to, make sure that I don't have to worry about that. Anyway.
Professor, how about me, Professor?
I didn't understand what you said, sorry. Parking passes? Kirby, as I've told you before, we'll just talk privately about it, but I have no good answer for you right now. If you're on that list of students that are supposed to show up next time for the lab, you know, as we discuss, are you on this list? Yeah. Well, you know, if you can't make it, you can't make it, and we'll deal with that later, right? Tutoring services this semester and last semester. I need to stop this. I'm going to stop the recording. Thanks, everyone. I'll see you all next time.